A single atom heat engine as a sensitive thermal probe.
Preparation and manipulation of quantum systems for the design of new technology require the ability to detect the influence of physical properties of their environment with high precision. However, many of the variables cannot be measured directly, as they are not proper quantum observables, and must be instead inferred from indirect measurement. The temperature of a system is such a property. On the other hand, the emerging field of thermodynamics in the quantum regime sheds new light on energy exchange processes between interacting small quantum systems and their environment. Manipulating these interactions in a structural manner reveals simple laws that relate properties of their environment to observables of the quantum system. For example, the power output of a quantum heat engine operating between two baths strongly depends on the temperature difference of the baths. Using this concept, we design a temperature sensor. To understand the working principle of our proposal, let us consider the following example.
Here, we see a water wheel that spins due to the river flow. In this sense, we can consider the river as an engine that produces work thanks to the water gradient. This output work is employed to move a wheel. In our quantum model, the engine and the wheel are replaced by a trapped ion. Its radial degree of freedom acts as an engine. The output work is provided by the temperature gradient produced by two separated thermal baths that interact with the ion when this is moved to these locations, leading to an engine cycle. On the other hand, this output work is transferred to the axial degrees of freedom that mimics the wheel and make the ion oscillate in this direction. Due to the coupling nature between the ion and the baths, the oscillations grow linearly every time the engine performs a cycle. The cyclic nature of the engine allows to transform small bath temperature differences into macroscopic oscillations of the flywheel. In an inverse perspective, measuring these oscillations allows us to use this engine as a sensitive thermometer. As the generated output depends on the relative temperature differences, if one of the baths is known, the other is fully determined.
Once we have explained the working principle of our model, now let's move to the lab for the experimental details.
This project started 2016 when we did the smallest heat engine with a single ion. Now this project is funded by the research unit Thermal Machines in the Quantum World, and the details are following.
In this lab, we are running a single atom heat engine. Our system is a single calcium ion trapped in a linear Paul trap. We did a modification to the Paul trap so that our radio frequency electrodes are tilted to the symmetry axis of the trap by a small angle. And this tilt induces a small coupling between the radio state and the actual motion of the ion. The working principle of the heat engine is as simple. Depends on the temperature of the radio state, the ion experiences a different displacement force in the actual direction. So if we periodically switch the temperature of the radio state, we excite a coherent motion in the actual direction, which serves as the energy output of the engine.
The cold bath is implemented by applying Doppler cooling to the ion, and a hot bath is employed by applying noise as well on the DC compensation electrodes. Then the engine is run for a number of cycles, and after this, by simply taking a picture for a brief period of time, we can estimate the position of the ion and therefore determine the growth of the amplitude and therefore determine the temperature difference.